Deploying an AI system marks merely the initial phase. The subsequent imperative is its sustained health and performance. In 2026, the silent degradation of AI models in production poses a significant threat, impacting operational reliability, compliance, and ultimately, business outcomes. Without continuous vigilance, even the most sophisticated AI can falter, leading to silent failures and substantial losses. This challenge necessitates a robust framework for monitoring AI systems post-deployment. The focus must shift from initial accuracy to long-term operational integrity. Organizations face a growing surface of potential silent failures, data exposure, and uncontrolled automation if they lack continuous, real-time monitoring of how these systems behave in production. Defining AI system health in 2026 extends beyond traditional uptime and error rates. It encompasses understanding if the AI is making sound decisions, treating all user groups equitably, and if its predictions maintain accuracy over time. This holistic view requires evaluating output quality, assessing for bias, and ensuring ethical considerations are integrated throughout the AI lifecycle. Key performance indicators for AI models in production are multifaceted. Beyond raw accuracy, metrics like precision, recall, and F1 score are critical, especially in classification tasks. For generative AI, evaluating faithfulness, relevance, safety, and hallucination rates is paramount. These metrics provide an immediate indication of a model's effectiveness in real-world scenarios. However, quantitative metrics alone are insufficient. Data drift and concept drift represent insidious threats to AI performance. Data drift occurs when the statistical properties of input data change, while concept drift signifies a shift in the relationship between inputs and outputs, or the meaning of the underlying data. Both can cause model performance to degrade silently, necessitating continuous monitoring. Operational performance also demands scrutiny. Latency, the time taken for a model to respond, and throughput, the number of requests processed within a given period, are vital for maintaining service-level agreements. Spikes in latency or drops in throughput can indicate bottlenecks or resource contention within the inference pipeline. Resource utilization and cost monitoring are increasingly important, especially with the scale of AI deployments in 2026. Tracking GPU/TPU utilization, memory consumption, and API token usage for large language models helps prevent unexpected cost overruns and optimize infrastructure. Efficient resource management is directly tied to the economic viability of AI initiatives. Anomaly detection in AI outputs moves beyond simple error flagging. It involves identifying unusual or unexpected behavior that may not be an outright error but indicates model degradation or even malicious input attempts, such as prompt injections. This requires continuous analysis of output patterns against established baselines. Observability stacks for AI now extend beyond traditional application performance monitoring. While APM tools track latency and error rates, AI-native observability platforms focus on output quality, evaluating metrics like faithfulness, relevance, and bias. Platforms like Confident AI, MLflow, and Arise AI offer capabilities like trace capture, evaluation, alerting, and drift detection specifically for AI workloads. Automated alerts and thresholds are indispensable for proactive maintenance. These systems trigger notifications when key performance or quality metrics deviate from predefined ranges or when drift is detected. Alerts can integrate with existing incident response systems, ensuring rapid intervention. Proactive maintenance strategies include regular retraining and recalibration. As data and concepts drift, models must be updated to reflect new realities. MLOps frameworks facilitate continuous model monitoring to operationalize drift detection and automate retraining pipelines. This iterative refinement is critical for sustaining model accuracy over time. Implementing updates safely requires controlled deployment strategies. A/B testing allows new model versions to operate alongside existing ones, comparing performance metrics before a full rollout. Canary deployments introduce new versions to a small subset of users, minimizing potential impact if issues arise. These methods prevent widespread degradation from new deployments. MLOps platforms play a central role in continuous optimization. They provide the infrastructure for orchestrating the entire AI lifecycle, from data management and model development to deployment, monitoring, and iterative improvement. Tools within these platforms automate tasks like drift detection, retraining, and version management, enabling a feedback loop that continually enhances AI system performance. Ensuring fairness and ethical AI monitoring has become a critical concern. In 2026, AI systems must be regularly checked for bias across protected characteristics to prevent discriminatory outcomes. This involves integrating bias detection and mitigation tools and ensuring transparency in algorithmic decision-making. Regulatory compliance and audit trails are paramount in 2026, with frameworks like the EU AI Act and NIST AI RMF demanding continuous verification of AI systems. Organizations must maintain detailed documentation of model architecture, training data, performance metrics, and decision-making rationale for auditability. Automated evidence collection is essential for efficient compliance. The long-term vision involves evolving towards autonomous AI maintenance. Adaptive AI systems, capable of continuous learning and self-optimization from real-time data, are emerging to proactively identify and remediate issues. This shift aims to reduce dependency on manual updates, ensuring AI systems remain robust, reliable, and continuously aligned with operational goals without constant human intervention.